Hello! In this class on relativity, we are essentially following Einstein's book chapter by chapter to explain his theories on special and general relativity. This video, however, is going to take a different tack. We're going to step back and look at it a different way. We're going to look at it with Euclidean geometry and vector analysis to show that if time is a fourth dimension with the same characteristics of the three dimensions of space, that length contraction and time dilation must occur. And we're going to show this in a way that is visually and intuitively easy to see, so you can get a feel for how these occurrences happen. Now, Einstein alludes to this a little bit in his book, but he, like most physicists, leans on the math to show how these things must be true. We're going to take that math and use simple geometry to give an intuitive picture so we can have a good feeling for why length contraction and time dilation must occur. Okay, so let's get started. First of all, there are two kinds of people that you will see trying to explain special relativity. One are people who try to use the propagation delay of light to explain what we see as length contraction and time dilation. For example, we might see someone who says, well, if we have an object traveling in this direction at the speed of light, and we are observing from this point right here, light from here reaches us sooner than light from there. So if this object is so long, well, as it's moving, by the time we see the light that reaches us from here, it has already moved over to here. And because there's less delay from the back than from the front, the object appears shorter. These explanations, and all of them that use the propagation delay of light as an explanation for length contraction or time dilation, are completely incorrect. The other type of people are physicists who use math to explain special relativity, and they are usually completely right, but it's not something that all of us can wrap our minds around. So what I'm going to do is show graphically what the math tells us in a way that we can intuitively see that these things must occur. First, let's take a quick look at the math. I'm not a mathematician by any means, and me teaching any kind of math at all is the blind leading the blind, but I do fairly well understand the Lorentz equations because they are simply rearrangements of the Pythagorean Theorem. I have another video that explains that, which I will link in the description below. So the Lorentz factor gamma is equal to the reciprocal of the square root of 1 minus the velocity of the object in question squared over the speed of light squared. And once again, I do have a video that shows how this is simply a rearrangement of the Pythagorean Theorem, which if we look at a right triangle, and the three different parts are the adjacent, the opposite, and the hypotenuse, the Pythagorean Theorem says that the length of the hypotenuse is equal to the square root of the adjacent squared plus the opposite squared. And you can rearrange that into this formula. So the Lorentz factor is simply a rearrangement of the Pythagorean Theorem. So we're looking at already that, we might be able to do something with right triangles to show how special relativity works. I'm going to be focusing more on the reciprocal of gamma, which is alpha, which is simply the reciprocal of that. So alpha is equal to the square root of 1 minus the velocity of the object in question squared over the velocity of light squared. And what that tells us is, let's look at that right triangle again. So we have a triangle with a right angle. Let's make this a 30, 60, 90. So there's 30 degrees, 60 degrees, and 90 degrees. I am using that because this is the geometry that happens if the speed is at 1/2 the speed of light. So we have the hypotenuse here and the opposite here, and this length here is going to be the length of the hypotenuse times alpha. So if we are going at 1/2 the speed of light, and the hypotenuse represents the speed of light, we're going to have the adjacent is going to be 0.866 of the length of the hypotenuse. So once again, here's the hypotenuse. This is going to be 0.866 times the hypotenuse. And we can calculate this out using the alpha formula. Plug in the numbers. We have the square root of 1 minus velocity squared over the speed of light squared. I'm not going to demonstrate the math because that's not what I'm here to do. But we will find out that if this is going to be 1/2 c squared, that our formula comes out to 0.866. So that's just simply a representation of that math. And another triangle I will use frequently is a 45-90 triangle, because this is kind of a sweet spot in this kind of math we're doing here. So we have two 45-degree angles and a 90-degree angle. And so this is what we get if our speed is 0.707 times the speed of light. And I like this because it's easy to remember the proportions, and so we can do our calculations, if you will, without having to do the math. So if this is 0.707 c, then this is going to be equal to the speed of light. So once again, the hypotenuse is representing the speed of light. This is going to represent our velocity, which is 0.707 times the speed of light. And our Lorentz factor, or our length contraction or time dilation factor, is going to be 0.707. So both of these sides are 0.707 times the length of the hypotenuse. And so actually when it comes to time dilation is going to be the reciprocal of this number, but we can look at it in such a way that this number represents time dilation, which we will be seeing in a few moments. So I just wanted to show that the Lorentz factor formulas are directly related to right triangles and Euclidean geometry. Okay, so let's set the stage here for our thought experiment that we are going to be able to show how length contraction and time dilation must occur if time is a fourth dimension and it is equivalent in its qualities to the three space dimensions.